Good morning. Today in CS 2420, we're looking at creating an actual object-oriented based array so we can actually look at how we can organize and work with an array as a structural component inside C++. As we're going to be building this from the ground up, so we can see similarly how an array itself can be created and referenced in a more object-oriented way, but still using the actual C++ structure of the built-in array data type. And so we have right here, we have our design diagram that's going to go over that. We're going to be using the template class type, aka the type or gang sign symbol type that we're working with, so we can actually work with arrays that can be storing any different kind of thing inside them. As you can see right here, we have a data member section and a methods and constructors section. Inside our data member section, we have two data members we're going to be working with. We have an internal array pointer, internal array of type pointer, excuse me. And so that's going to be the actual array that is at the heart of our data structure we're going to be working with to actually make that happen. And that's of type pointer because truly what we see in C++ is that an array is stored as a pointer of some type. And we'll see this as we actually look at the code here a bit more closely. We also have a size data member, and that size data member, of course, is going to be of int because, again, we're working with things we can actually handle really quick with our structures. We don't have to worry about long, but that'd be the next type that, again, that we'd be looking at if we want to make this be more expandable to do things that have to have more than 2 billion entries. But we're good at right now with 2 billion, so we're okay. We have 3 different sections in our methods and constructor section. We have a constructor, a copy constructor, as well as a destructor. And so we have to actually work about how we're going to be handling the memory that's going along with that. And that's why we have a destructor here with this. We have a regular constructor that automatically takes a size as a parameter. And then we have a copy constructor, so we can copy an array into a new object right there. And so we're going to be using that to make a copy constructor using the copy swap idiom. And then we have some operators we have to work with. We have the assignment operator, the equal sign, and the square brackets and square brackets again. So we have 2 different square bracket operators we're working with. As you can see, they are different, however, by the return type. One is a type reference, the other is of type, and we'll see what's going on with that. Basically, it evaluates into be the left-hand versus the right-hand side version of how we use the square brackets. And finally, the idea of having methods, we can actually use this. We have our getSize method, our getFromIndex, and setItIndex methods. So we can actually use a method to access our array data structure. So that's what we're actually going to be building with so we can look at the actual array itself. So let's go look at the code that goes on with this. This is going to hide inside our linear folder, which is inside our structures folder, which is inside our model, because that's where we're actually building this inside here. And so we have our array.hpp. And so array.hpp is the actual class we're working with this. As you can see right here, I have a hash include for assert.h and iostream. Assert.h, of course, is so we can verify that what we're putting inside our data structure, we're using values that will work and won't cause memory problems, because we can't access negative space. We can't go backwards. Negative space might work in some fictional universes, but here in the real world, we have to actually have a number value for things. And then iostream, I have that hash included because if we want to actually trace this and see what's going on inside the code, we use that so we have debug statements right inside our code. It's a great way, especially when we're building our data structures, so we have the ability to have it right there and available for us. We're also going to have using namespace std, so I have access to the built-in data types like strings, cout, stuff like that. Again, that's for the idea of tracing and debug. If we're actually waiting to use this in other things, that would only happen inside the other classes where we use that. But since we have this as a beginning level class, we're working with that right here so we can have that. As we get more advanced, that will be just simply hash included or using in the classes that are going to be implementing these data structures themselves. We then go to, of course, our hashtag ifndef / hashtag define. That's where we use the preprocessor to actually tell what's going to happen. This is array.hpp, so it's hash ifndef array_hpp because we can't have a dot inside our hash ifndef line. And then we have right here actual class definition. So I've got quite a bit of comments attached to this. So we can see right here on our template class type is attached to the actual class itself. So the entire class is templated. So we have that going along with it. We have our class, its name is array, because again, we want to name things what they are and what they do. And inside our array class, we have 2 sections of visibility. We have our private section and our public section. Inside our private section, we have the data member internal array, and that's a type pointer. Because when we're working with C++, the way we actually store an array of information, especially as a data member, is by declaring it as a type pointer. Because what happens when we're using an array inside C++ for code purposes, if we want to just have a reference to that, it's simply a type pointer, and then the actual length of that is how much memory gets attached to that pointer, so we can build the array. Because again, when in C++, our array itself is actually a contiguous chunk of memory. And so that type pointer says, oh, it has at least enough memory for that spot. But then when we allocate the new memory in the heap, it's a contiguous chunk of memory for that type. And so that's where that comes into play. Our size data member, oh my gosh. For some bizarre reason, C++ arrays don't know about size, but our object-oriented array, it does. And so we have a data member called size, and we have a getter for that as well. We have our constructor that goes along with that, as you can see right here. It's an array of type, and we have a parent size that goes along with that. And then we have our copy constructor. Our copy constructor takes a const array as a parameter. We're using a const array reference right here, and so we can tell it's const means we're not going to be able to modify it. And then the reference keyword symbol, whatever we want to use, the ampersand, that we're talking about that. What that provides for us is it means that we're going to get the actual reference to that memory structure. So we can actually go and grab that thing, the actual thing for it, not just a copy of it, and we can then get a constant, so we're not going to change it, and go and get all the actual values out of it. Our destructor is specified with the tilde key in front of it, so the tilde key is that little shift and the key next to the 1 on the keyboard, and we'll be using that for all of our destructors. It's a special thing that we'll be using inside C++. We haven't had to worry about that in Java and C# or Swift because the memory handling is automatically handled by either the operating system, the virtual machine, or what's going on behind the scenes of the language itself. But in C++, we must explicitly handle our memory allocations, and so we must write our destructors for this so we can actually deal with that. Then one of the special things about C++, one of the things that can make things confusing as well as figuring out how to actually work with it, are operator section. And so again, we're using prototypes right here. Again, you notice that this is simply just a line with a semicolon, no actual implementation attached to it. Even when they're simple, I like to keep my class definitions just prototypes only because that way I know exactly what's happening. But we have our prototypes for our operators because we're going to tell our operators, we're going to overload them. We're going to tell them how to operate in a different way. In this case, how to operate with an array of type. And so we have an equals sign and 2 sets of square brackets. And so we have our type reference operator with square brackets and a type operator with square brackets. And also the type operator with square brackets itself without a reference is a const because it's going to be it's unchanged because it's a copy for that. But we'll see what happens with that in just a minute. And then we have the actual methods because, again, we have an object-oriented class, and so an object-oriented thing has methods that refer to things. And so in this case, we have our getSize method to retrieve our size data member. We have our getFromIndex and setIndex, which will perform the same functions that we would see with our square brackets if we use a traditional array, but using it in a more object-oriented style, aka we have a dot and a method attached to, or in our case, when we're working with a pointer, a selector operator, and the method call after that. And so let's go take a look at how we're doing for it. So we first have our constructor. As you can see right here, every block of code that we're working with in the implementation section of a templated class will start off with template class type inside angle brackets above that line. So we're going to see this line over and over again. So get used to it, get comfortable with it, get ready to write it a lot. And so I'm using type as a word for this. It could be anything. You could write template class G, P, Q, R, S, V, blah, 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 but type reflects what we're doing. And again, we want to make sure our code is something that can reflect what we're doing and explain to not simply ourselves what we're doing, but anyone who comes by and reads our code, whether they're a programmer or not, they can actually get an understanding of what we're doing inside our code. And so it's really key that we use words and things that make sense, that reflect what we're doing. And so I actually take the time to write the word type because that way I can know it's of type thing. Because a type is a word that everyone that speaks English, when we're talking about things, we can explain, oh, it's this type of thing, it's that type of thing. It's a word that means something of a type, so we can explain that really well. Inside our constructor, though, we start off with the assert command. Assert says if this doesn't pass the test, close the program right now. This is basically like throwing an exception immediately in Java. And so what this is doing is that we're going to make sure that our code only operates in conditions that are guaranteed to work properly. In this case, I assert that size is greater than 0. So this parameter has to be greater than 0. There is no need to make an array of -8. Doesn't make sense. Can't put -8 times a value and actually get a contiguous chunk of memory. -8 is not a storage amount. We don't do that. And then 0, making an array of 0, for this purpose, when we're using this data structure, there's no reason to make an array of 0. We want to actually make arrays of some specified size. It's a fixed structure that has that many spots to hold things. And making an array that can hold nothing doesn't make any sense for what we're working with this. So we're not going to allow zeros of possible value. So once we've passed that assert statement, we then go and we assign size to be our data member. We use this selector size so I can talk about the current object, this, and use the selector operator, aka how I can use the this pointer in C++, and I assign that variable size into that. And that's also because of the fact that I'm using size as the same name as the data member, because I like the idea that I can explicitly tell what's going on with that. Finally, after I've assigned the size, I then have to allocate a new chunk of memory. And so I do that using the new keyword in C++, and then type array square brackets size. So I'm allocating the memory for that. And so this is the same line we'd normally see to make our C++ array, but we're doing this internally inside our object-oriented array, so we can have that right there. So our internal array has the same style of making just some array that we could use inside C++. It's just a nice little wrapper class to go on that. We have our copy constructor right here. And so our copy constructor we have, again, notice we have our class name, array of type, and so that's the scope, and then with scope resolution operator, so it says this is the class, followed by the scope resolution, and then specifying that it's the copy constructor. We know it's a copy constructor because I have a parameter that is of the same type, array of type, as the actual thing itself. So I'm creating an array from an array. Okay, no big deal. And so the first thing I do when I make a copy constructor is I have to assign the size of this parameter to be the copy's get size. Now, because of the fact that I've already created this other array, I already know that this assert statement has already been passed, so there's no reason to reassert that right here because it's already implicitly asserted with that structure. Then I have to actually build the data structure itself. So my first thing I have to do is, of course, the same line right here, internal array is a new type size. That same structure right here, internal array is a new of type, passing it size. So I allocate enough memory for it to happen. And then what I do, because I've got that reference right here, I'm going to go through and grab each of the copies of each of those values inside that reference location and say internal array at this index is going to get a copy of 2 copies value at that same index. So I'm copying the value from here, putting it over there, copy, paste, copy, paste, copy, paste, putting those values all the way over there for the size that's actually that structure. And so that's what a copy constructor is designed to do, is take this one, make a copy, put it over here. So I've made a new thing, okay? No big deal. Regular thing we'll do in C++. We then have our destructor. Now in our destructor, as you can see right here, I added a couple cout statements. Like I said, that's why I used that hashtag include IOStream and the using namespace std so I can get access to the cout and indel keywords so we can use that information for it. And what this does is it's a nice explicit way I can show what's happening inside my destructor. So again, template class type happens again. And then I have right here array of type, the class that I'm working with, scope resolution, and then the tilde indicated is the destructor. That's always going to be used for when we're working with the destructor. And then cout, so I'm about to delete the structure itself. And then I have the delete keyword. And because I'm deleting an array, I use the array keyword as well, followed by the array that I'm actually deleting. And so what that does is it'll deallocate all the memory that's attached to this array variable. And so if it was simply just a pointer, it'd just be delete and then the pointer variable. But because it's an array, I use delete and then the array keyword so I can make sure I can delete all the references that that array is attached to. And then after that's done, I have a cout statement saying internal array has been deleted. This is just a nice little thing so I can see that there's a result of this happening, so we can actually see some code working with this. And so you have a nice little visual, oh, that's been deleted from the actual structure. Memory is no longer being allocated for this array. We then have our operators. Our first operator we're going to look at for the overload, and again it's called an overload because we're changing the way that the actual operator itself works inside C++. Other languages don't support this, like Java, but C++ allows us to change how an operator will work with every data structure we want to use. And so in this case, I'm overloading the equals operator. And so as you can see right here, the equals operator returns an array of type reference. So it gives a reference to another, a reference to an array, so is what it's assigning into that. And it takes as a parameter a constant array. And so when we're using the assignment operator, we want to make sure we're not actually talking about the current operator. That would just be a waste of time. So if I'm talking about the current array, I don't need to do any of this code. I just return a reference to this. So if the address of to assign is not equal to this, then I have to actually go in and do stuff. If it is equal to this, I just simply return a pointer to this because that's a reference to that what we're working with. Okay, I dereference this. But if it's not this thing that I'm working with, then I want to go ahead and check to make sure my size doesn't match. If my size doesn't match, okay, if size is not equal to assigns get size, then I'm going to delete my internal array because I have to actually reallocate memory. And so to do so, I must also delete memory that's attached to that. Then I'll assign my size to that new value size and recreate my internal array parameter to be the appropriate size of memory. And so if my size was this big and I'm copying, I'm assigning a new operator that's this one, it gives me the ability to free that chunk of memory. If my array was this big, I'm copying this big, I'm deleting this little chunk that I'm no longer using and allocating enough memory to use the bigger structure. And so this way I'm not wasting memory and I don't leave myself open to a memory leak or some other problem with inside my program itself. And so that's why I have to deallocate memory if my sizes don't match. If my sizes are the same, then I don't have to worry about that because I'm automatically going, oh, it's already the same size, I just have to copy values. And that's what we happen right here in this next step. I'm just going to use a regular for loop. I start off at 0, go up to less than size, going up by 1 each time. Standard approach for a for loop to go iterate over an array. And for each spot in that array, I'm going to copy the value from to assign into internal array. No big deal. My assignment operator works just like that. Easy peasy stuff to do. Excuse me, please. Finally, once I've done with all that structure, I simply return a dereference value of this because that's a reference to the array that I just changed. Okay, so I've got that in, so I've assigned that into it. So that's what we're doing with this. So we are overloading our operator to assign into first. We then have our 2 square bracket operators. Our square bracket operators, what we're seeing with this is the idea that it's the left-hand side versus the right-hand side operator. So it's basically how are we using the square brackets? Are we using the square brackets before the equal sign here on the left-hand side or after the equal sign on the right-hand side? The first one, the left-hand side right here, is assigning to the reference, aka it's actually affecting the actual memory storage of that location. So type reference is the return type of that. And it's an array of type is the class that we're working with, followed by scope resolution, operator square brackets. And the parameter inside that square bracket is an int. Is what we're passing, and that's the index. So within this, the first thing I have to check is I have to assert that my index is a valid number. When I assert my index, it's a compound assert statement that we have to work on. I first have to make sure that my index is greater than or equal to 0, because of course I have to make sure it's not a negative number. That wouldn't work. But then, not only does it have to be greater than or equal to 0, so 0 is okay, but I also have to make sure the index itself is less than size. So I can't try and refer to things that don't exist. So I always have a guaranteed value that's going to be a valid location within my data structure, something that's not going to cause any exceptions to be thrown or cause my program to crash. So I'm asserting within this to make sure it works properly. And then, just like regular C++, all I do is I use the return keyword followed by the array that I'm working with, in this case, internal array, and then the parameter that I'm looking at the index that we're looking at. So this is just like go into the internal array inside C++, scroll over to the index of that array, and grab that value. And so we're using a way of actually doing this. This is the same operations we happen inside regular C++ array if we were using this on our own. It's just a way of actually doing this in a more object-oriented way, and we can actually see what's happening behind the scenes. So it's the same basic structure. We're actually just making it so we can explain it and see how it works inside that. Now, the difference on the right-hand side, instead of a type reference, because I'm affecting the actual value, I'm just getting a copy of that, and so it's just a type. And so by doing it as a type for the return type, it just gives me a copy, because when C++, when I give something back, it's just a copy of that value. And so, and again, it's, note that again with const, because I'm not going to be changing it, it's just going to get a copy of that so I can use it right there. And again, that same assert statement happens right here, where I'm asserting that the value is greater than or equal to 0 and the index is less than size. Has to still be a valid location. And the return statement is exactly the same as well. The only difference is that at this time I'm returning a copy of that value instead of a reference to the internal value. So it's the exact same code. The only difference between the left-hand side and the right-hand side of the equal sign is the left-hand side I'm getting a reference, aka the ampersand. On the right-hand side, it's a copy, aka it's just a copy of that value at that location, so I can have access to it. And so left-hand side versus right-hand side, not a lot of change in the code, it's just how we're actually using that. And so we can use work with that. We then have our hashtag basic section, aka the getters. And so we have our get size, and oh my gosh, look at this. The get size works just like every other get we've ever written, and it has just simply return and the data member we're working with. Wow. Now this way my array is not totally hipster. I actually know how big I am, unlike a regular C++ array that has no concept of its size, and I have to pass a second parameter reference to size, or have some constant defined earlier in my code because I didn't know that. Right here in our object-oriented array, we know our size because we're going to refer to it with our getSize method. We have some access to that. And it's a const because we don't need to change it. So we've got that, so it's returning a const value. That also comes back up to this lovely reference right here when I'm using the assignment operator and the copy constructor, because those are constants, so I have to make sure that size value is valid for that as well. And then my getIndex and setIndex methods, the regular regular method-based access to an array, so I can actually work with the array as if it were an object that has a dot, and I can get inside it and work with it, unlike Java or C++ normally. And so I have a void type, which is the setIndex, because it's not going to give me anything back, it's simply going to assign a value. So it takes the parameter for position and a type item. And note that I'm using the int pos right here instead of index, because it doesn't matter what I'm using up here. So up here in my actual description, I have int index in that parameter right here that I'm actually working with this for getIndex and setIndex. But when I come down to the actual implementation down here, I have a variable of pos, because the variable name inside the formal declaration of the prototype has no relationship to the name of the variable inside the actual definition of that method. We can use anything we want right there. So we have our int pos and type item, so I'm going to set this item at that position. And so again, I have that same assert statement I've been doing. I make sure that assert is guaranteed to be greater than or equal to 0 and that position is less than size, making sure my index I'm working with right here, the variable, is a valid number within the size of my array. If it's not, throw it out, crash burn my application. Finally, I go as internal array and then passing it that same pos parameter, and I assign item into that location. So it works just like what we're doing up here when we're actually going through and copying the values into this right here. We're just grabbing that parameter, putting it into that location. Same exact thing right here, I'm just using it and putting it inside the internal array. When I'm using the getFromIndex method, again, I'm going to return a copy of the value that's stored in that location, hence with the type, return type right here. Again, I have that same assert statement I've been working with all over, where assert index is less than or greater than, excuse me, or equal to 0, and index is less than size, and I should put a space right there and make it look nice and pretty. But same assert statement we've been working with the entire time. Nothing different between this assert statement and this assert statement. It's just the variable name that I'm using. Doesn't matter which one I'm using, just whatever works for me. I then say that type value, I'm going to get a reference to that internal array at that index and assign it to the variable value. Once I've got that, I will return that variable so I can have that over and send it back. And so that's what we're doing for this, to actually return the type array. And so again, what we've done right here is we've just gone and it created an object-oriented version of the array data structure inside regular C++. We just made it so we can actually access it with methods right here, the getSize, getFromIndex, and setIndex. So we can actually treat it more like an object-oriented thing versus simply just the square brackets, which is a little bit old school from C. But we still made it so we can actually handle that square bracket access inside our class. We can actually handle it like a regular C++ array because we've operated to make sure that this class array can overload the way that square brackets works. We know how to use them. We did the same thing to overload the equal sign so we can actually replace a value inside that. And so we've made it so we can actually use an array in an object-oriented way, but it's still actually at the heart is still just a regular C++ array. It's just a nice little object-oriented wrapper on top of it so we can see how it works and how to actually build a data structure inside C++. And so again, taking a look at that object-oriented array right here. Again, here's our design. We can see that we have the internal array pointer reference because that's what arrays are at the heart of C++, and then the information that we're going through to actually look at that. And so we have our object-oriented array that we've made inside C++. We'll continue on with these data structures and look forward to this so we can see how a list, a dynamic data structure works. We'll be using that as an abstract base class, and we'll be using it with a linked list, stack queue, and a circular list so we can see some more advanced features with that. And so that's what we're going for, and we'll continue on with this as we go through the structures. Thanks, and have a good day.